Hello, my name is Tommy, and today we're talking about VSEPR and hybridization. So what are the molecular geometries of CCl4, SF4, CO2, H2O, and ZeF4? So I've already have the Lewis dot structures on the board, so we can just get right to the molecular geometries. So CCl4 has 4 domains, and none of them are lone pairs. So it's going to form a tetrahedral shape, where there's no odd spaces because they're all filled in without lone pairs. So CCl4 ends up being tetrahedral. SF4 is a little different in that it has 5 domains, and one of them is an electron, or is a lone pair. So that lone pair kind of pushes everything else down and forms a seesaw. So it looks kind of like this. With the lone pair up here. And that's a seesaw. CO2 has no lone pairs on the C, so it ends up being linear because these electron domains of the oxygens equally push each other apart, causing just a straight line, looking a lot like that. H2O, which is kind of tucked into the corner, and I'm very sorry about that, but H2O is very much like a tetrahedral, except 2 of them are lone pairs. So it ends up looking like that. And the angle between these is about 109.5, or a little less than that, because these lone pairs push those hydrogens down and cause it a bent shaped. For ZeF4, it has 6 domains. So what happens is that these fluorides kind of get pushed in between these lone pairs and causes a square plane where it's flat, but those lone pairs kind of stick out up and down. That makes sense. Now we're asked to see which of the following molecules are polar. So the same molecules from before, just which ones are going to be polar and nonpolar. And the way you can tell with their molecular geometries is by if they're symmetrical or asymmetrical. So CCl4 being tetrahedral is symmetrical. Everything is evenly distributed. So CCl4 would be nonpolar. SF4, everything's asymmetrical. Those lone pairs push everything down, and therefore it's the atoms, if you just look at it with the atoms in mind, it's asymmetrical. So that one, SF4, would be very polar. CO2, everything is spread out and there's no lone pairs pushing it down, so CO2 is nonpolar. H2O, we can see the lone pairs push those hydrogens down, so the thing is asymmetrical and polar. ZeF4, while lone pairs do kind of push everything around, remember, it results in a flat square plane where all of them are equally distributed. So it's still symmetrical and therefore nonpolar, even with those lone pairs. So sometimes orbitals will merge with other orbitals in order for them to have more bonding sites, which happens with carbon with its S and P orbitals. So, because normally carbon would only be able to bond with 2 because they completely fill up the S orbital and then half fill the P orbital. But in order to bond with 4, carbon will merge the 2 and half fill an sp3 orbital with 4 electrons. And that way it can have more bonding sites. So what the end result is hybridization. And we can have sp, sp2, and sp3 depending on how many domains carbon has. So let's look at a few molecules here and see what the hybridization is. So for methane, the hybridization would be sp3 because we have 4 domains. so sp3. Now for carbon dioxide, it would be sp1, or just sp, because we have two domains. For carbon monoxide, it would also be sp, because we have the triple bond here and the lone pair here, so two domains bond with the carbon. For C2H4, both carbons have the hybridization of sp2, because both of them have three domains of the two hydrogens and the other carbon. For cyanide, the hybridization would be sp, just like carbon monoxide, because we have the lone pair and the triple bond. So you can kind of see the pattern where however many domains you have, subtract 1, and that's the number with the p. So we have 4 domains here, p3. 2 domains here, p1. 2 domains here, p1. 3 domains here, p2. 1 domain here, or 2 domains here, p1. And then just put an s with it.